Okay, so here is our second problem. So our second problem is we're going to have a collision. This guy's at rest. That's cart 1, which is on the red if you remember. And cart 2, which is the blue, that's going to be moving and it's going to collide, bumping into this guy here. All right? So this guy moves off to the right. And if you notice, with cart 2, it bounces back a little bit. Not a lot, but a little bit. Okay? So we're going to go through the same exact process where we're going to measure the velocities for each. Knowing the masses for each, we'll calculate the momentums for each using the equation momentum is mass times velocity. Knowing their momentums initially, we'll add them up to get the total that we start with. And if we know what we start with, we know what we end with because momentum is conserved. Say it. Good job. All right. So then the final situation, we'll measure what this guy's velocity is and calculate what this guy's momentum is. And knowing this momentum and the total, we can solve for the one's final momentum, and knowing one's final momentum and its mass, we can solve for its velocity, and we'll see how that compares with the data. Okay? Got the idea? Feel free to pause it at any time. Okay, so let's get this on LoggerPro. Bang. Pull LoggerPro right up. Okay, so we should be good to go. And let me hit collect. Here we go. Okay. So let's take a look at it. All right. As you can see, we have the blue. That's cart 1 going fast. We have the collision, and there's some momentum swap going on. Notice the blue now has a velocity in the opposite direction. Also notice the red's velocity is smaller than the blue's initial velocity. So it wasn't complete 100 transfer velocity. Keep in mind this has more mass, so it's not the velocity that gets transferred, it's the momentum. More mass, less velocity. But notice this still has some on the other side. So let's analyze this and let's see if momentum was conserved. We're going to go through the same process we just talked about. We're going to calculate this guy's momentum before, calculate the momentum after, and predict what this momentum is and its velocity and compare. Okay? So first thing we need to know is how fast cart 2 is going before the collision. So I'll highlight that, I'll click on stat, and we're doing this for velocity 2 only. And let me just move that so you can see it. And there it is. So we've got an average right here. I don't know if you can see it, but we'll round. So that's 0.43. Okay? So we're going to write that down. And that's blue. 0.43 meters per second before the collision. Okay? And we still have the mass. That's 0.51 kilograms. That hasn't changed. So go ahead, calculate its initial momentum. Knowing the mass is 0.51, knowing the velocity is 0.43 meters per second, multiplying to get the initial momentum that we start with. Okay? I'll give you a moment. Feel free to pause. Okay? Cart 1, that's the red one, still got a big mass of 1.02 kilograms. It's initially at rest. Momentum is mass times velocity. Go ahead, calculate its initial momentum. I know, it's some hard math. Okay, so pause if you need to at any time. We're then going to calculate the total momentum we start with by taking this guy's momentum and adding it to this guy's momentum to get our total that we start with. Okay? Next thing we need to know is if we start with that much momentum, how much do we end with? It should be equal because momentum is conserved. Say it with me. Momentum is conserved. So we need to know how fast 2 is going in the opposite direction after the explosion. So let's look at that. So that's still the blue. So nice constant velocity there. I like it. All right, so we're going to get the stats for that. And here we go, I hit stats. And we're still doing it on velocity 2 only. And here we go, A's for velocity 2. That's this piece here. I don't know if you can read it, but it's negative, should make sense, it's going the opposite direction, 0.085, okay? 0.085, negative. So let me put that in there, 0.085, negative. So negative 0.085 meters per second, okay? Not very much. So what you're going to do, take mass 2, hasn't changed, multiplied by velocity 2, negative 0.085, to get 2's final momentum. Okay? So, and we don't need this piece because we wrote it up there. We don't need to rewrite it. Okay. So, we know the momentum that part 2 has. We know the total that they should have because momentum is conserved. What we start with equals what we end with. So if we know the total, and we know 2's final, do the algebra to solve for P1 final. Okay? Do the algebra to solve for P1 final. If we know these two, subtract to get this guy. So this plus this has to equal that. And now that you know, and again, pause at any time, P1, we know M1, you can solve to get V1 final. Bang, 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 bang. So go ahead, pause it, get caught up with your calculations. You should get a positive number for your velocity because it's going towards the right. Figure out what this is, okay? Go ahead, pause it, and do your calculations. Okay? All right. So now let's see what we actually get for a velocity there. Let's go over to here. I'm going to do the same idea. I've got this highlight area. I'm going to do stats for the red. We want to find out how fast that red is. So I guess I have to, there we go. And we want to do it for, not position, velocity, there we go. And we're going to do it for velocity 1 only, because that's the red. I hit OK, here it is. And we get an average value, I don't know how well you can see it, but positive, I'm rounding, 0.24 meters per second. So how does that compare with what you calculated? We get an observed average velocity of positive 0.24 meters per second for the red. Pretty cool, huh? Okay, so now let's do our final piece, okay? Our final piece, what we're going to do, and let me get this last piece, is we're going to take two cars, collide them, and they're going to stick together and move off as one unit. So I don't know if you noticed when you were using these before, there's actually some Velcro on this. And that way, make sure we're on the track, they hit, they stick. Although we're going to keep with our same givens, we're going to make part 2 heavy, and this is our collision. And they move off as one giant mass. So our strategy is, just like before, we're going to measure this guy's velocity before the collision. This guy's at rest. And we can figure out its momentum of each before the collision. The mass hasn't changed, 0.41, 51, 1.02. And knowing their individual momentums, we can calculate their total momentum. And if we know the total momentum we start with, we know the total momentum we end with. Because momentum is conserved. Good. So now let's talk about the final situation. This is one giant blob, this thing. This thing can be thought of as one giant mass with one velocity. And if we know the momentum of that thing, because momentum is conserved, then we can solve for its velocity. Got it? All right, like I said, you can pause at any time, rewind, etc. So let's go through this, all right? New piece of data here. We can get rid of all these so we're not staring at them. This is the old data. Okay. Let me hit collect. We're live. And there we have it. Okay? So let's look at this. See what we got. We want to analyze this piece right here. So our initial velocity, part 2, which is the blue, Let me get my stats. And I want to do it for just 2. Okay. So again, I don't know how well you can see that, but this is an average of, we're going to round 0.40 meters per second for this piece here. By the way, notice that slower. Notice how that was slower? Well, it's a mass. That momentum has to get shared between the two masses, so that means it's going slower. So we got 0.40. Let's put that in our data. So this is positive 0.40 meters per second. Okay? Again, pause at any time, rewind. Mass is 0.51. The velocity is 0.40. Go ahead, calculate its initial momentum. Pause while we wait. Okay? Do it the same thing. Momentum for cart 1. Its mass is 1.02 kilograms, and it's initially at rest. Do that hard math. So then, we know 2's initial momentum, we know 1's initial momentum. Do the math to add to get the total momentum we start with. Pause. Okay? If we know the total we start with, we know the total we end with because, say it, momentum is conserved. Good. So, if we know our total momentum that we end with, and we know this giant mass of these two numbers combined, and its velocity. So divide both sides by mass, so the velocity should be that final momentum of the thing divided by the total mass. So momentum divided by mass gets us our velocity. Okay? So go ahead, do your math, pause it, and then we'll look at what we actually got. Okay? So let's look at our actual values. Let's highlight this region. This is the region we're interested in after the collision. And I hit my stats on that. And we can do it for either one of them. Should be the same. It's one mass. And we get 0.099. I'm rounding. I'm sorry, I lied. Down here. Average of 0.11 meters per second. So we're averaging that together, and that gets you 0.11 meters per second. How's that look? All right, don't forget all your answers. Go on the survey on the link below. All right, and make sure you've got your work on a piece of paper. That's fine, but I'm checking off your homework by your completion of that survey where you put your answers. All right, thanks, and good luck.